Let us try to visualize what the whole matrix would look like if we were to order rows and columns in such a way that similar rows would be next to each other and similar columns would be next to each other. Visually, this amounts to going from this picture to that one. In this cartoon, there are only 2 blocks, but in reality, we may have more blocks and they also may overlap. Each block corresponds to a group of users and a group of movies that are homogeneous. For example, it could be that this group of users would tend to rate this group of movies a bit higher than the rest of the movies or a bit lower. It could also capture a bit more complicated pattern that is different from the rest of the matrix. The key mathematical observation is that a matrix with a block structure can be decomposed as the sum of simple matrices, one for each block, if these matrices are different enough. We can efficiently recover each of them using a numerical algorithm called singular value decomposition, or SVD in short, even when the matrix is only very partially observed. Let's see what this simple structure is. For that, assume for simplicity that our matrix has only one block and that it is located on the top left of the matrix. Here, the red part is the pattern we are looking for and the blue part is the rest. For example, the blue part corresponds to only ratings from the central clusters. 3s with probability 1/2, 4s with probability 1/4, and 2s also with probability 1/4. However, assume that the red block corresponds to bikers and dense movies. As we all know, bikers have a thing for dense movies and tend to rate them a bit higher. Let's say that they rate them 4 with probability 1/2, 5 with probability 1/4, and 3 also with probability 1/4. So in average, 1 point higher than the central cluster. If we call B the blue matrix, then we can actually represent the superposition of the blue and the red matrix as the sum B plus U outer V, where U is a column of the same height as B and V is a row of the same width as B. Specifically, U is a column with only zeros and ones where the ones indicate the user is part of the bikers group. And V is a row with only zeros and ones where the ones indicate the movie is about dancing. We say that U out of V is the outer product between column U and row V. We say U outer V. Unlike the inner product, the output of an outer product is a matrix rather than a single number. It's easy to compute. The number of rows in the output matrix is the number of entries in U, and the number of columns in the output matrix is the number of entries in V. Next, the entry of the output matrix in the ith row and jth column is simply the product of the ith entry of U, Ui, and the jth entry of V, Vj. In the case of U and V that are only zeros and ones, as we described, we get exactly a matrix with only zeros entries except for the top left corner that has only ones in it. It is clear now that B plus U outer V corresponds to the matrix that we have described. Then we can add more blocks. B plus U1 outer V1 plus U2 outer V2 plus U3 outer V3, etc. We can add one outer product for each block. It turns out that the vectors U and V don't have to be made only of zeros and ones, but may represent more complicated patterns such as polarized tastes. For example, if they take value 1 on one group and -1 on another group. To illustrate this example, consider 2 groups of Netflix users, which we can safely consider to be disjoint: bikers and teenage girls. Then consider 2 groups of movies, 80s dancing movies and pop concert. Next, take the column vector U with 1s for the bikers and -1 for the teenage girls and 0 for everyone else. Take the row vector with 1 for the 80s dancing movies, -1 for pop concerts, and zeros for all other movies. What does the outer product U outer V look like? Right, it will have 1s for the pairs biker 80s dance movies and 1s for the pairs teenage girls pop concerts. It will also have -1s for the pairs bikers pop concerts and teenage girls' 80s dance movies. This indicates that while bikers tend to like 80s dance movies more than the average Netflix customer, they tend to dislike more pop concerts than the average Netflix customer. The opposite is true for teenage girls. Of course, more complicated patterns arise in practice. Given that our matrix of interest has a decomposition of the form B plus U1 outer V1 plus U2 outer V2 plus U3 outer V3, etc., it turns out that it's not too hard to find the pairs UJ-VJ using what is called the singular value decomposition, or SVD, as long as there are not too many such pairs, even if we only observe a small subset of the matrix. This is because the SVD is very robust to noise. In a way, each pair corresponds to a stereotypical rating pattern. If we allow too many such pairs, we have no hopes to recover the underlying matrix, but in practice, these matrices are nice. It is believed that there are about 15 such pairs for the Netflix matrix. To be more precise, the Netflix matrix has probably many more pairs, but it is well approximated by such a simple matrix. In the case studies, we will see how the singular value decomposition can tell us how to identify how many pairs are relevant for a given problem.